Okay. All right, so we're in rigid body kinetics. We're talking about moments of inertia. Oh, son of a bitch. That was 17 minutes. That's a little long for YouTube Friday. 17 minutes is a little long. Or too short, depending on... See, that's where you can bring that, again, that's something you can bring to a party tonight. You can bring those videos with you. I do have some issues with the vertical videos, right? That's why you don't do vertical videos, because, you know, that's terrible, right? That's terrible. It would be way better in landscape. Okay, so we were talking about moments of inertia. We need this because somewhere we need to take into consideration how mass is distributed about an axis, because how much moment we put on it is going to cause amount of rotation. So just like mass is a resistance to translation, moment of inertia, moment of inertia is a resistance to rotation, right? So something that has a bigger mass moment of inertia is going to need a bigger moment to get it to rotate, okay? And so that's what we're talking about. So there's, you know, the fundamental definition of it is this integral of r squared dA, or dm rather. It's r squared dA for the bending, the area moment of inertia, but it's r squared dm for this, right? And so we went through and we actually applied the integral to a simple rod like this, and then it came up with what the equation was, right? This guy right here, for the mass moment of inertia of a rod about this axis right here, about the y-axis. It's also going to be the same about this axis as well, because it's either I rotate it this way or I rotate it this way. Those are going to be the same. But then if I rotate it about this axis, there's a lot of concentration. All the mass is concentrated around that axis, and so essentially it ends up being zero, especially compared to the other directions, right? And then we said, well, if I grab it by the end as opposed to the center of mass, if I grab it over here, I should have a higher moment of inertia, and we carried that out with this. And we said, you know what's really nice is there's a bunch of shapes that already exist. Somebody else has already gone, the book has already gone through and developed these moment of inertia equations for different shapes. So here's all the different shapes. Mainly what we're going to do in 2D stuff is going to be these rods. I think there's a couple discs that we do and a couple of plates like this, right? These, these we'll get into when we do 3D stuff, these other ones, right? And then you also notice that there is another one, these 3D ones, not only do they have these guys right here, just some foreshadowing, instead of just IX, IY, and IZ, they also have these things that are right here. These other ones, X, Y, YZ, and ZX. Foreshadowing, those things are called products of inertia. And we'll deal with those later when we do 3D in just a couple of weeks, right? Again, we're in the end of week 9, so we're more than halfway there. We're almost partway there, okay? The method of composite bodies. So, you know, are you gonna find objects that look exactly like those images? Not necessarily, right? And so we're gonna use this method of composite bodies, or the parallel axis theorem, to build these things up. For example, the first problem we're gonna do, the first problem we're going to solve with this methodology is this right here, right? It's a rod attached to a rod. So if you have something like this, you're not going to find in the text, so you're going to have to make your own moments of inertia using the parallel axis theorem, right? We'll kind of keep it simple in that regard. We're not going to get too crazy, but we do have to do it. All right, so how do we do that, right? We use the method of composite bodies. So if I wanted, right, so if I've got this blob over here, here's my blob, and I wanted to determine its moment of inertia about a different axis, right? The equations on the previous page they give us the moments of inertia about its own center of mass, or a part of it, like, you know, the end of it or something. But if I want to get it about another axis, right, I can do that. And I do that with this equation right here. This looks very familiar to what you're using for area moment of inertia. It's the moment of inertia of this blob about this axis over here. So if this is rotating, it'll be doing a big rotation around like that. I can figure out its moment of inertia around that. I just do the area, or the mass moment of inertia about its own center of mass. That's what the prime denotes, right? And then I add on to it its mass, the mass of that object, times d squared. And d is the distance, the parallel distance, right? The perpendicular distance between the two parallel axes. So perpendicular distance between the two parallel axes, it's that distance, and that distance squared. That's exactly the same equation that you use for the parallel axis theorem, except for instead of m there, you see an a in area moment of inertia. Okay, so IO this is the of inertia about axis. Ooh, I don't know why I capitalized it, but I did. LO. Right. This is the I center of mass. The prime to denote this is a little redundant, right? Object center of mass. Right? The center of mass obviously denotes that, but also the prime denotes it as well. Mass of object. We'll apply this in a second on a couple different ones. And then D is perpendicular distance between parallel axes. I watched a little bit of my video the other day, and it's really weird, the typing part. Do you guys ever see that? If you watch one of the videos? Because the typing, you can't see, but I have a keyboard come up, but when you watch the recorded video, you see the keyboard come up, and then you just see, buttons being pushed. Maybe it's just me. It's just me. It turns out it's just me. Quit looking at me so silently and judgingly. I hate that, fuckers. Don't do that. You guy's an idiot. That's what I... Okay, so what we do, here's the method for doing it, right? I lay it out. I took this right out of the text. Choose the parts. Try to divide the object into parts whose moments of inertia can easily be determined, right? Determine the moments of inertia each part, and then add them together, right? Sum the results together. Like I said, we'll do an example. A very simple example would be, let's say, if we applied it to just this simple rod, right, which we did before. Like I said, I'm not spending too much time because we're not going to do too much of this. There's a couple little ones that we do along the way. But so if I wanted I about the y-axis, we'll say the y is over there. If I wanted I about the y, I could say it's the IY prime. That's the center of mass one plus MD squared. Right? Obviously, we already did this once before. We actually calculated it before, and this one is actually given in the text. But I just wanted to show you at play here. So then, if I was to apply this here, IY prime, we determined earlier and can look it up, is ML squared all over 12. That's the moment of inertia about its own mass center. And I add on to it M, and the distance would be from here to here, right? That would be L over 2 squared. L over 2 squared. And if I carried that out, I would get ML squared all over 3. Right? If you just simplified those fractions, that's what you would get. Right? Because this distance right here, right, that's L over 2. And that's the perpendicular distance between the parallel axes, right? Because you'd have your y prime axis is going up like this, right? And then the y is going up like that. So that distance is that distance in between there, which would just be L over 2. Okay, let's apply it to a more complicated one. So we got this guy. This is a more interesting problem. We've got 2 slender bars of length L and mass M. And we're asked to find IZ about O and IZ total. Right, so it's asking us for the moment of inertia about, right now we're in 2D stuff, so all of our moments of inertia are coming out, right? The axes that we're rotating about are all going to be about the k-axis because everything else is in the xy. So everything's being rotated about this axis, coming out this way. So you'd have one axis coming out at O. So we're trying to find what I is about that. And then we're also going to figure out what I is about the composite mass center, right? So this is one of those objects. We're not going to find this in a table, right? This shape is not going to be in the table. So we would have to, we're not going to find that in table. So we're going to have to look this thing up. Okay, we're going to have to composite it. We're going to have to break it up and use a method of composite bodies, right? So I'm going to break up my 2 objects. There's one object right here, and there's going to be another object right here, right? The 2 slender rods there. I don't know why I squared it, okay? And so again, we're after the moment of inertia about this axis and the moment of inertia about the whole object's center of mass. At some point, we're going to have to calculate it. The first part says I about O. So let's figure out I about O. right? The first few times I do this, right, especially if I were learning it, I think a common thing to do is you make a little table, right? And in this table, we'll have the I, which object we're looking at. We'll have M of I, and we'll have D of I, and then we'll have I, center of mass of I, and then we'll have I, Z of I, right? Which is going to be equal to I, center of mass of I, plus MI/DI squared. It's just, you don't have to do this each time as you get better at it. You don't have to do this. Just when you first lay it out, sometimes it's nice to do this. Okay. So then let's look at the first. So I've set it up like this. I got the first object, right? The mass of the first object, does it tell it? It has mass M. So this is just going to be M, right? DI is the distance, right? It's, again, this is the parallel axis theorem. So you think about the axes coming out. So it's the distance between the center of mass of each object and O. So the first center mass would be right here, right? That center of mass, and it would be coming out of the board, and we're trying to get it about O. So the distance would be between here and here is what that distance would be, right? And they have the length L, right? So this would just be L over 2. Okay, this is just, right, this is a slender rod, and the center of mass of a slender, or the moment of inertia about the center of mass of a slender rod is ml squared over 12. So this would just be ml squared all over 12, right? And then the last one is where I actually apply the parallel axes, which would be ml squared all over 12 plus m times L over 2 squared. This is what we did on the previous page, actually. And so the total here would be ml squared all over 3. Right. That's for the first object. So the first object's moment of inertia about O. So it'd be this guy's moment of inertia about the end. You might notice that, like, could I have just jumped? Like, this is something that's in a table. A slender bar with its moment of inertia about its end. That's in the table. If that's in the table, I could skip this and go right to this. Just saying, I know this object's moment of inertia about its end is just ml squared over 3, and then you could just write that down. Okay. But if we didn't notice that, we would have to calculate like this. So then you go to the second object, right? The second object. So the second object has the same mass. Its distance now. Now we're looking at the distance. This guy's moment, center of mass is right here, and then O is right here, and they're both coming out of the board at those locations, and so it's the distance between those two axes, right? And so in this case, that would just be L. Right? That would be L right here, and then again, the moment of inertia of the object about its own center of mass is ml squared over 12. And so then this last one would be ml squared all over 12 plus m times L squared. And here we end up with 13/12 ml squared. Right. Now, once you get each of those objects about O, you just add them together, right? Because this guy, right, this one right here is this object's center moment of inertia about its end, that point right there. And then this one right here is this object's moment of inertia about point O. And as long as they're both about point O, or axis O, then you just add them together. So if you added these two together, right, those things added together, we get, I got rid of my fractions, 1.417 ml squared. Right? You're not going to find that in a table, right? You're going to have to build that thing up. Okay? Like I said, sometimes it's nice to do this little table. Do you have to do the table each time? No. Right? But when you first start learning it, it's a good idea to do that. Same thing, you could use the same type of table in area moment of inertia as well, just slightly different equations. I know that historically, you guys don't like it. I'm going to copy this, because we're going to do the next part. Okay, second part, so that's A. B says find IZ about O. No, part B says IZ total, IZ prime total. And so about its center of mass. Before I could do that though, I need to figure out what the center of mass is. I don't know what it is yet, right? We haven't calculated that yet. Okay, so let's do that. Center of mass in the y direction is easy, right? The center of mass in the y direction is just, right, this is symmetric about the y, that's symmetric about the y, so it's just gonna be 0 is what the y direction is gonna be. But the x direction is where we're gonna find, it's not straightforward, right? So we do x bar, right? This is the weighted mass, is a sum of xi, mi, so it's just a weighted average. Right. So it's the weighted average between the distance to the individual object's center of masses multiplied by the mass of each individual object divided by the total mass. So what this would look like in this particular problem is the distance for the first object, for 1, okay, here's 1, the distance between its center of mass and usually you start with the reference point. I'm gonna use the reference point right here on the left, and we're gonna go that direction. And so the distance between that reference point and its center mass is just L over 2. L over 2 times M. Now we go to the other object. The other object, that distance is between here and that reference point, which is over there. So that distance would be L. L times M. And then you divide by the total mass, which would be, in this case, 2M. Right? There's 2 masses. If you carried out that math right there, this becomes 3/4 L. Okay. And so that tells us that 3/4 L from the reference point. You can pick anything to be your reference point if you want. I could have picked it, my reference point as being the right-hand side. I picked it as the left-hand side. You could have picked in the middle. And the answer you get is the distance between that reference point and where the center of mass is. But since I did my reference point here, that just means 3/4 L is where I'm going to hit that. Right? So my center of mass will be this, 3/4 L. This is where that center of mass is. Okay, now once I have that, then I can come down to my table here and work that out. Right, so this I, we do the first object. The mass is M. The distance I now, the distance is now between the center of mass of each individual object and now the new center of mass that we just found. So it'd be between here and here. Right? That's the distance that goes in there. And that should be 1/4 L. Right? I center mass of the object is ml squared all over 12. And then this last component would be, right, it's just the ml squared all over 12 plus m times 1/4 L squared, right? And this ends up being 7/48 ml squared.
On the step above,
Yeah.
can you explain how you got L over M?
No, I did that wrong. I mean, it's L times, no, it is L times M. L times M. I wasn't done yet. I was just gonna say, Mark, what do you think is wrong with this equation? I'm trying to fly through it, but when you fly through it, I just didn't want to spend too much time because I think you guys have seen stuff like this a lot. Is that correct? Right? Statics, mechanics, material, right side, left. So this is my right side, but you're your right side, right? L times M. See, I can't do it. I gotta call this one the right side. I can't go left side. What do you think? Did I do that right now? Okay. Thank you. Okay. And then you do the next one. You go to the next one. 2m. Again, L over 4. That'd be the distance between here and here. right? The axes coming out. Later on, we'll get to this later. You have a homework problem. Do you have a homework? Do you doing these on your homework? I think you're doing did you moment of inertia in homework? No, next one? Okay, all right, never mind. Next week, you're gonna have a homework problem that deals with this stuff, right? And you gotta be careful. I'm gonna just show you a little foreshadowing for next week. Is like when we do this one, right? There's this guy and then there's this guy. And again, remember the axes are coming out like this. So if I was trying to figure the moment of inertia about this axis right here, what the distance that I care about, that's the D that you would use for this problem. And so when you get to that, if you started over the weekend, you just be careful of that because it's the axes, you picture the axes coming out, it's the distance between the axes. And so there's one where we go about this end here and you just gotta make sure that you know that that's coming out of the board and the D that you care about is that D right there. Okay. Back to this. This guy's just ml squared all over 12, and this would be ml squared all over 12 plus m times 1/4 L squared. And again, this is 7/48 ml squared, and the two added together. So once they get them about the same axes, you just add these things together. This ends up being 0.292 ml squared. Is the total moment of inertia of that object about its own center of mass. And sometimes, I mean, another bit of foreshadowing as well, and students mess this up quite a bit, is like, well, why would I want this I about O, and when would I ever want I about Z? Like, why would I want the differences, right? And actually, these are the two that the two that really matter the most are about, so if I was trying to figure out, the accelerations or how this thing rotates about O, then I would have to calculate the moment of inertia about O. But if for some reason I was trying to figure out how this thing is going to rotate about the mass center, like what kind of alphas I'm going to get and omegas I'm going to get about the mass center, what I would care about would be about the mass center. So it depends on where you're summing your moments about. There's going to be a step, just like you did before. I sum in statics, you sum the moments and you set that equal to 0. Well, now things are moving. They're not going to be equal to 0. They're going to be a little foreshadowing. And some of the moments is going to be I times alpha, right? Is what we're going to end up with. And I is going to be, which I you use is where you're summing your moments about. If I sum my moments about O, I'm going to need I about O. If I sum my moments about the mass center, I need I about Z, or about the mass center, or Z prime, I guess, okay? A little foreshadow. So you're going to have to calculate these along the way. Okay. And then, all right, we're ready for this. Okay, everybody cool with that? I mean, like I said, just go back through it. I think you've done this several times before. I wanted to fly through it. Maybe I flew through it too fast, made some mistakes along the way, but I did. But I wanted to. Let's cranking it out. No questions. No questions today. Yeah.
Was it 1/4 like L squared?
Yeah.
Not 3/4.
Yeah. Great question. Manus.
Yes.
Hell yeah. That's 3 people. We got Nate Dogg. We got Manus. We got Logan, we've got Mark and Derek, and that's it. Give me another one. Oh, we've got cheerleader, right? Throwing people around. What is her name? Nate. Oh, there's a couple Nates. Nate Dogg. We got Nate Dogg and Nate. Maria. What is it? Shit, man. Oh, that's bad, right? That's really bad. Fuck. One of the 5 girls in here, and then, right? My bad. Yes. Clearly, that's. Yeah, that's. What's your name? Jermaine? Yeah. How interesting. Okay. Jermaine and Maria. And then I've added a couple. And I will immediately forget them. Okay. What was I talking about? Why did I even go?
Wait, the question.
Oh, you had a fucking question. That's That's what it was. Okay, so again, what it is, we're looking, the D that you use is the distance between the center of mass of the object you're looking at and the axis that we're trying to take the moment of inertia about, right? So the center of mass of object 1 is at L/2. It's right here, okay? It's right here. That's the center mass of object 1. And then we're trying to take it about the center of mass of the overall object, which is right there. So this to here, that's 1/4 L. Cool? Yeah. And then this one, then the other one ends up being 1/4 L because now it's between this point here and this point here. And so so that's L minus 3/4 L, and that puts us at 1/4 L for that one. Cool? Yeah, okay, see, look at that. I do know what I'm talking about. Okay, so side note, me and Chad had a discussion about, see, this is great. Me and Chad were talking, and I was like, hey, can you, literally just say, hey, could you tell me, because there was lots of questions about units of power, and actually units of work and units of power, because I myself was confused. I was like, oh, what is it? I can't just throw that at you. It's like, oh, well, we have foot-pounds, but then, and then horsepower's in there somewhere. Well, let's discuss this for a second, okay? So work is a joule, right? That is it's the amount of energy that it takes to when you apply 1 Newton over 1 meter. That's a joule. Isn't that beautiful? That's a beautiful definition of it, right? So that's a joule. All we get, we don't even get anything. We just get a foot-pound, right? In English units, just a foot-pound. So it's how much energy it takes for 1 pound. It's how much energy is used when 1 pound pushes something 1 foot. Okay, and so that's just a foot-pound. That's how it relates to a joule, right? And then a watt, right? A watt comes in, and its power is something different. That power is energy over time, is what it is, right? And so a watt is 1 joule per second. And so I think that's isn't that great? Because it's just straight up like that. Well, again, when we start talking about it in English units, we have horsepower, right? And what is horsepower? Well, it's 550 foot-pounds per second. Why? I don't fucking know. Somewhere along the line, so it's like, how strong is a horse? Right? That's what we did. I guess that's what it is, right? Like, how strong is a horse? I don't know.
I think it's how fast or how much a horse can lift a certain weight with a pulley.
Right, yeah. Right. So lame, right? So weird. It's so weird, but that's what it is. That's the difference between horsepower and that. And then there's there's the relationship between the two, right? And so, but also, side note, what's another unit of energy as well? Of power. Sorry, power is a calorie. A calorie is also but it's usually calories are usually used in terms of thermal stuff. But it has the same units as a joule, and they can actually be related as well. And I did have a chat with Chad about, hey, could you add that? And so I have another table somewhere that has calories included as well, but that's another unit. But again, we're just so dumb. We're so dumb for using our units, right? Okay, so then what we got 4 minutes. So real quick, I'll show you where we're going. So next thing is, like I said before, we have forces and we're gonna have moments, right? We're gonna have forces and moments acting on our objects, right? And we're gonna start out with F equals ma for solving these problems, right? We're gonna have almost right away, especially if you start out with 3D or even 2D, that's still gonna apply. We're gonna still have F equals ma. The only difference is, instead of just being any old A location, we have to say what location it is. And that G there stands for center of mass. Why? I don't know, right? They chose center of mass in this thing. So we're gonna get at least in 2D stuff, in planar stuff, we're gonna get 2 equations of motion out of this. Sum of the forces in the x, sum of the forces in y are equal to mass times acceleration of the mass center, right? That only applies to the mass center. If this thing was off center, if this force wasn't acting through the mass center, it still applies. You still have that. Where the off-center part comes in is if it's off-center, it's going to be causing a moment about the mass center. And so that they're going to be separated into 2 different things. So what we're going to do is, we get 2 equations out of this. We need a third equation. That third equation, after a little bit of derivation, ends up being, actually 2 pages later, it ends up being, actually 3 or 4 pages later, it ends up being this, right? It just ends up being our third equation is going to be sum of the moments about either a fixed point, and if it's sum of the moments about a fixed point, is just IO times alpha, right? Again, what we're going to be after is this alpha here, or we're going to be given alpha and we're going to be after a moment, one of the two, right? Or this one down here may apply too. If you're summing the moments about a mass center, it's just the same equation. It's just you use the moment of inertia about the mass center. So the only difference between these two equations are if you sum about a fixed point, you use the moment of inertia about the fixed point. If you sum the moments about the mass center, you use the IG about that. So that's what we're after. So we're going to have three equations. So the way we solve these problems are exactly the way we did in particles. It's just now we got three equations, right? We have a moment equation. Some of the force in the X, some of the force in the Y, and some of the moments either about a fixed point or about a mass center. And then you write down those, you draw a free body diagram, you write down the equations of motion, you do kinematics, which are more complicated now, right? Because the kinematics is what you're just dealing with right now, right? How things are rotating about people, and you're working your way around and you're doing all this. That we still have to do that because that's our kinematic step. And once you apply the kinematics, boom, you could solve the problem, right? So examples of the types of problems we would solve. This is a little rod thing. It's starting out at rest. We release it, right? And then it asks when we release it, what are our reactions over here? And then what is the alpha is what we're after, right? Because it's gonna drop, right? But it's gonna swing when it drops around, and it's gonna cause certain reactions there. It's not just gonna be statics on what the reaction is over there because things are moving, and so it's gonna pick up some stuff here. Here we got this guy. This is just, you think this is kind of like particles, except for the difference between the particles. This has some mass. It has some resistance to rotation, so we have to take that into consideration. What's going to be interesting about this is what you do in statics, that this force is equal to this force. In this case, that's not going to happen. There are going to be different forces on either side of it because the difference between them is going to get this thing to rotate, right? A little foreshadowing, a little more foreshadowing. This is a log. This little log, we're going to yank on the base of it, and it's either gonna fall like that, or it's gonna tip over towards us, and we're gonna have to figure out how to solve that one. And then we're gonna go into work energy, right? So and then how you do work energy for these types of problems. And then, guess what? Impulse and momentum, just like we did before. And what's really nice is it's super analogous. What we learned in particles, the same processes gets used in this 2D rigid bodies as well, right? Same process. It's just every step is just a little bit more complicated. Okay, cool, break.